Okay, today, operations with vectors in R3 now. After we've set up the two-dimensional case, the three-dimensional case is no big deal here. It's really nice working in R3. First of all, magnitude of an algebraic vector in 3 space. To find the magnitude of a vector in 2 space, we use the Pythagorean theorem with the triangle formed by the vector and its x and y components. We can use the Pythagorean theorem to determine the magnitude of a vector in 3 space. Look at this. Amazing. If you've got a vector u equals a comma b comma c, if you want to find its magnitude, you use the Pythagorean theorem, but in 3D. Look at that. Square root of a squared plus b squared plus c squared, where the c is the z component of the vector. Now, the proof is not part of this course, but I put a PowerPoint up on the website that you can check out that proves this. It's such a beautiful proof. Feel free to take the time to walk through it and try and understand each step along the way, but you're not responsible for it in this course. What you are responsible for is knowing that it works in 3D. And so then if you want to find the magnitude of a vector in 3 space, your job is you go, okay, magnitude of u equals square root of 2 squared plus 4 squared plus negative 1 squared. And I get square root of 21, which doesn't reduce. I want you to watch out for those reducings and the radicals, but in this particular case, root 21, that's the best we can do. That's all there is to it. Alternate representation of vectors in R3. I mentioned this in the last lesson. As in 2-space, linear combinations of unit vectors give us another way to represent algebraic vectors, and a powerful way. It may not seem like much at first. This i's and j's things is pretty good. The only difference today is I is 1, 0, 0, because we're in 3-space. J is 0, 1, 0, because we're in 3-space. And then k is the unit vector along the z-axis, 0, 0, 1. Those definitions are in the box there. But basically, if you want to write a 3D vector in i's, j's, and k's, you take the x component, and that's how many i's you get. You take the j component, oops. You take the j component, and that's how many j's you get. And you take the k component, and that's how many k's you get. You just got to indicate how far along the I, the j, and the k, how far along the x, the y, and the z axis you want. And the I is how far along the x, the j is how far along the y, and the k is how far along the z. Operations in 3 space. When working with algebraic vectors in 2 space, we developed the operations of addition, subtraction, and scalar multiplication. Now we extend them to 3 space. And look, it's all exactly the same. If you want to add 2 vectors, you add their x's, you add their y's, and now you add their z's. You want to subtract 2 vectors, you subtract the x's, you subtract the y's, you subtract the z's. And if you want to do scalar multiplication, you just multiply each of the x and y and z component by the k value out front. Let's jump ahead to the example here. It says prove that u plus v equals x1. So it says prove this thing right here using this right here. And I'm going to use the i's, j's, and k's to show off how good the i's, j's, and k's are. So here we go. Let me just, my keyboard might jump ahead here. I'm just flipping things around here. Okay, so if I want to do u plus v, what I'm going to do is switch to i's, j's, and k's here. I've tried to keep the screen on so you can see above exactly what u is. So u is x1 I vector plus y1 j vector plus z1 k vector. And then v is made up of x2 I vector plus y2 j vector plus z2 k vector. So all I've done is make up u right here in terms of i's, j's, and k's. I've made up v right here in terms of i's, j's, and k's. And now I'm just going to reorder the addition because addition can be done any order I want. So I get x1i plus x2i plus y1j. I'm going to go over and get the other j, y2j. And then the k's, z1k plus z2k. And combining those, I get x1 plus x2 times I. I've just common factored out the I. And then I get y1 plus y2 j. I've just common factored out the j. And I get z1 plus z2k, and that's equal to x1 plus x2 is the first component, y1 plus y2 is the second component, and z1 plus z2 is the third component. So, very easily with i's, j's, and k's, I've proved the addition here. To do this geometrically can be done, but it's very, very challenging. It might even be intuitive, but the i's, j's, and k's really streamline the procedure and make it very easy to do these kind of proofs. Anyways, to actually do the operation, it says find u plus v here, u plus v, add the x's, 7, add the y's, -5, add the z's, 3. So nice. You just do the same thing with the z that previously we did with the x and y. This one says find 3u minus 2v. So I got to go 3u minus 2v. 3 times the u, which was 2, -3, 4. Minus 2 times the v, which was 5, -2, -1. Scalar multiplication just does exactly what we'd hope it would. You just multiply the 3 by each of the components in the vector here. So I get 6, -9, and 12. And I get minus 10, -4, and -2. Maybe you'd want to multiply in a -2, and then you'd have to add the two vectors. It doesn't really matter. You got to deal with that negative at some point anyways. And so I go 6 minus 10, I get -4. I get -9 minus -4, I get -5. And I get 12 minus -2, which is 14. And it wants the size of that. So over here, magnitude of 3u minus 2v will be the magnitude of -4, -5, 14. I'm using the Pythagorean theorem in 3D here. Square root of -4 squared plus -5 squared plus 14 squared. Grab my calculator here. Trying to do it in my head at the same time. 16 and 25 is 41, and 196. I think it's 237, but just make sure. Plus 14 squared, 237. And that's it for today. Operations in 3D, so nice. Check out that PowerPoint if you want to see the proof.